Okay. And well, here are our notes from last time. Got them here somewhere. Right. We did a lot of computation here, right? Looking at tabulating input-output values for the secant function, which, first I compute the cosine and then I compute its, good morning, Taylor. I see you here. And make a note of that. Yeah. Okay. And maybe I should have the chat open here so I don't miss things, or I'll try to keep up with this. So today is 11/12. Before 12/13. That doesn't make sense. That would say that the 12/13 is the day before 13/14, which there is no 13th month, not yet anyway. I had proposed that we have a Trump month, but really that's not likely to fly. The exchange would be, we'd have an 8-day week. Don't play with the calendar. Okay, so we were looking at the secant function, which is the reciprocal of cosine. So we have the reciprocal of, say, the cosine of pi over 6 is square root of 3/2, right? Dial it up, right? That'd be 2 over the square root of 3. And we talked about how computing 2 over the square root of 3, if you were to do it, by approximating the square root of 3 as a 4-digit approximation, that would lead to this sort of computation, long division, very difficult. Whereas if instead you rationalize the divisor by multiplying by 1 in the form of √3 over √3, then you get twice √3 over 3. It's easy to approximate twice √3, that's 3.464. And then it's easy to divide that by 3 and you get a value of 1.15, et cetera. So yeah, it can be somewhat painstaking to do these computations, but if you make a careful plot of input-output pairs and use the symmetry, what symmetry? Well, secant is the reciprocal of cosine, which is an even function. So secant is also an even function, right? And so it's got y-axis symmetry. So while we have this branch over here, its reflection would also be part of the curve over there, right? Reflected through the y-axis. And so then we looked at tangent of pi over 4, which was 5.4, number 25. And, we computed some input-output pairs. But the first thing is to determine the period. So that the natural period is pi. So if you divide pi by pi over 4, you get 4, which is the period for this, expanded. It's actually stretched a little bit horizontally, so that the asymptotes range between -2 and 2, or the function, the asymptotes are at -2 and 2, and the interval between those has length 4, which is one waveform for the tangent function, which repeats ad infinitum. And what did we do then? We looked at, this was, 1/2 secant of 2 pi x minus pi. So we should factor out the 2 pi and see there's a horizontal shift of 1/2, vertical compression by a factor of 2, horizontal compression by a factor of 2 pi, and a shift to the right, didn't put the T in shift, by 1/2. And we did some input-output pairs, looking at where are the vertical asymptotes, right? For secant, the vertical asymptotes are where the input is equal to pi over 2. So if we set the input equal to pi over 2, so the input is 2 pi x minus 1/2, set that equal to pi over 2 and solve for x, you see that 3/4 is a vertical asymptote for this horizontally compressed function. And it's both compressed horizontally and vertically, huh? And so the other vertical asymptotes were if x is 1/4, well, that's, you know, do we get the wavelength for this thing? Yeah. It's 1, right? Or sorry, yeah. 2 pi divided by 2 pi is 1. Yeah, and so as you go from -1/4 to 3/4, that's 1 unit of length. That gives you 1 up and down. That's a complete waveform for the secant function. And you're going to have asymptotes at 1/4 and 3/4, then halfway in between you'll have another asymptote at 1/4. And you know, so what I did was find the vertical asymptotes and look at the midpoints between those. That's where your max and min for the secant function will occur. And that was that. Okay, so I thought we had also done an inverse function. I don't see it in my notes here though. 11, 12. Okay. That's today. Okay. So let's take up with some inverse function activities. Let's go back and read the text, and then we'll come back to the workbench here, works and problems. So what do we see? Well, the inverse of sine and cosine. Okay, there's the inverse of tangent, huh? Do we talk about the inverse of sine and cosine? So we have to restrict the domain, right? So for sine, we restrict the domain to the largest interval containing 0. Kind of makes sense where it's 1 to 1. That's going to be the interval from -pi/2 to pi/2, right? This little section of the curve. If we restrict the domain, we get a piece that's 1 to 1, and the largest piece, you know, close to the origin makes sense to choose. For cosine, you can't have an interval containing the endpoint, since any interval containing the endpoint will not be 1 to 1, right? So what we do instead is take the interval from 0 to pi, and that's this little section where we get an inverse, right? And the inverse tangent function is the largest interval that would make sense for that is the same as for the sine function, right? Where -pi/2 to pi/2. And on that interval, if we reverse input and output, we get a curve that looks like this. So this is a graph of the, are we looking at that? Okay. Okay, so I have to click on this in order to get focus over here. So yeah, this is a graph of the inverse tangent function, also called the arc tangent, because, you know, as you're saying, what is the arc that would produce this ratio of y to x, right, on the unit circle? A little confusing, right? Because these are not the x and y on the unit circle, right? This is like y is arctan or inverse tangent of x. It's sort of generic names for the input and output of a function. The generic input is x, the generic output is y. Those are not x and y on the unit circle, however, which is where we define tangents, so things get a little confusing. I will give you that. No dogs on campus? So the inverse secant, cosecant, and cotangent functions, yeah, those are just a mess. What can I say? Okay, so yeah, now look at, that's just crazy talk. Same thing for cosecant. Now, cotangent is a little bit more reasonable, but I think we're ready for some exercises. Good. So should we just jump in here to number 4? What is the arc that would correspond to a ratio of, or a y value of -1? what arc on the unit circle would produce a y value of -1? Well, that would be a clockwise arc. And it would be -pi/2, right? That would take us to -1 on the unit circle. So this value is -pi/2. What arc on the unit circle would take us to +√2/2? Well, that's going to be pi/4, right? Are you getting familiar with these places on the circle? Should we draw a circle? Let's have a circle. Okay, so I'm going to draw, for the purposes of, we'll use those to find these. Okay, well, I guess I just need to, okay. So here is a nice circle. It's very round. I'm going to draw our coordinate axes on there. And this is the unit circle. So this is going to be the point 1, 0, corresponding to a distance 0 from that position, right? So if you're saying that here we're at 0, -1, right? So that means that the angle, I want to say the arc on the unit circle that will take us to -1. That's the way you want to think of that. Arc on the unit circle will take us to a y coordinate of -1, right? Because y is sine on the unit circle. That would be -pi/2, right? What arc on the unit circle will take us to +√2/2? Well, that's here, right? And this arc here is pi/4, right? So this is pi/4. We got a bunch of these. Number 5, what arc on the unit circle will take us to a cosine value of -1? Well, that's going to be pi. Recall that the domain of the range of the inverse cosine function is from 0 to pi. That's how we read the domain of the cosine function from 0 to pi. That becomes the range of the inverse cosine function, right? And that's over here, right? So if we go an arc pi on the unit circle, that takes us to where the x coordinate is -1. How about 1/2? Well, 1/2 on the x-axis is about here. What arc, that would correspond to this point on the unit circle here, right? What arc is that takes us to, so that's this arc here, and that's t = pi/3, right? That's going to take us to a position where x is 1/2 and y is √3/2, right? Okay. So pi/3. Yeah, so how about what arc takes us to a tangent of -1? Yeah. Well, let's see. Tangent is the ratio of y to x, right, on the unit circle. So we want y and x to be opposites. That's true in the 4th quadrant here, where we're at x is +√2/2 and y is -√2/2. So the ratio of y to x is -1, right? And this arc here, well, the length of the arc is pi/4, but it's in the clockwise direction, so we refer to that as -pi/4. Right? So they just have a whole lot of these, and it's good to practice. So what arc would take us to a sine of 0? Well, that's 0, right? What arc would take us to a cosine of 0? Well, that would be pi over 2, right? Up here, the x-coordinate is 0. I mean, the x-coordinate down here is also 0, but that's not in the range of the inverse cosine function, right? So shall we remind ourselves what all these ranges are? So for sine, f of t equals sine t. Let's see, if we use t, then we avoid this cognitive dissonance of x and y meaning different things, right? So t is what we call the distance that we go on the arc of the unit circle, right? So for we restrict domain to the interval from negative pi over 2 to pi over 2, including the endpoints, right? Then the inverse function, which we denote, well, you can denote it in a variety of ways, right? Well, y, sine is y, right? So how about we rename this input parameter here y? Then it makes it more clear what we're talking about on the unit circle, right? There, okay. So what arc takes us to a y coordinate on the input here, right? So has range negative pi over 2. So remember, when you talk about the inverse function, you reverse domain and range. What used to be the input is now the output, and what used to be the output is now the input, right? Okay. And how about for cosine? So let's say for g of t equals cosine t, restrict the domain to the interval from 0 to pi, including the endpoints. Then g inverse of x is denoted, this is the notation. This does not mean the reciprocal, right? If it were the reciprocal, it'd be the secant function, and that's a common confusion, right? Has range 0 to pi, right? Because you swap domain in the range. What's the domain of the inverse cosine? It's the same as the domain of the inverse sine, which are, all the x values on the unit circle are between -1 and 1, right? All the y values on the unit circle are between -1 and 1. So, yeah, so the domain of the inverse cosine is the same as the domain of the inverse sine, and that's the interval from -1 to 1. It's the same as the range of the sine and cosine, right? How about tangent? Okay, so for, should we call it h of t? I don't know, equals tangent t. We restrict the domain, again, to negative pi over 2. Now, we don't include the endpoints because those are vertical tangent lines where the function is not defined, right? Then h inverse of, what do you want to call it? Y over x? Yeah, I'm kind of tempted to call it that. Yeah. Do we have another name for it that's good? Tangent? Could actually. Let's just call it U, all right? Has, and this is denoted again as inverse tangent like this, right? That doesn't mean the reciprocal, right? That means the arc that would take us to that ratio of y to x, right? Has a domain, range, sorry, consistent with my previous statements here. And that's the range is from negative pi over 2 to pi over 2. And we can make tables of values for sine. Okay, so if this is t, this is sine t, then we can say here's y and here's inverse sine y, right? So we use parentheses. And so we restrict the domain to negative pi over 2 to pi over 2. So negative pi over 2, negative 1. That means that when y is negative 1, the arc that takes us there is negative pi over 2. What are the usual suspects? So negative pi over 3 takes us to negative square root of 3 over 2. So the inverse sine of negative square root of 3 over 2 is negative pi over 3, right? And negative pi over 4 takes us to negative square root of 2 over 2. So here, if we have negative square root of 2 over 2 as the input, then the output will be the arc negative pi over 4. And negative pi over 6 takes us to negative 1/2. Negative 1/2 then will lead to the arc negative pi over 6, and then 0, 0, right? And all of these can be plus or minus, right? Where the plus corresponds to a plus and the minus corresponds to a minus, right? So same thing here, right? Minus or plus or minus, I don't know. So just by symmetry, we get a bunch. So now let's plot those points this way. Let's see. So I want to be between negative pi over 2 and pi over 2. So let's say here's negative pi over 2, and here is pi over 2. Perfectly evenly spaced. So this is going to be the, the arc sine. That's another way of saying inverse sine. Oh, arc sine of y, right? Just to be, use the familiar unit circle variables here, which means that this is the y-axis now, right? So what arc, let's see, so, oh, I screwed up already, didn't I? See, it's always, yeah. See, so now the outputs are between negative pi and negative pi over 2 and pi over 2, right? And so what are these inputs? Well, these are going to be negative 1 and positive 1, right? That's the domain of the arc sine function. Okay, what is the range? Well, yeah, I kind of wish I'd scaled this a little bit differently, but that's all right. So here's negative pi over 2. That means that this is positive pi over 2, roughly. And so we have negative 1 produces that, and positive 1 produces positive pi over 2. Oops, a little bit off. And what about the points in between? It wants to look like a sine curve, right? So what does that look like here? Well, let's plot some points in between. How about negative 1/2? All right, so if the input is negative 1/2, then the output is 1/3 of pi over 2. So that's going to be like here. So chopping these into 3 equal pieces. Get that, and we get this point here. So it looks like, yeah, it's like a sideways curve. It looks like that, right? And if we were to continue on, it would not satisfy the vertical line test, right? So that's going to be what the sine curve looks like. right? So the same thing with arc sine. So maybe let's spend a little bit of time on GeoGebra here to get a feeling for this. Do we have GeoGebra around here somewhere? Yeah. So let's get rid of these guys, and we'll have say sine, and I have to use the generic variable x in GeoGebra, okay, and arc sine, also known as the inverse sine, and I'm going to use the same generic variable, right? So does this look like what we just did? Well, it's all about the scale, right? So if we do this, yeah, then it starts to look more like just what we just graphed, right? Especially if we also do this, right? And then shall we restrict the domain on this thing? So I'm going to say if x is between -π/2 and, sorry, if x is between -π/2 and pi less than or equal to sine of x. Right, so then okay, so what are we looking for here? We're looking for that symmetry, and in order to see that symmetry through what? Through the line y equals x, right? Okay, so there's the line y equals x. Should we make it a dotted line? Because it almost looks so much better if it's dotted. Object properties, I'll say style. You can't see these menus, but trust me, they're there. So we get this, right? And yeah, so right about there, we see the scale on the x-axis is the same as the scale on the y-axis. And there we don't see so much distortion, right? It really looks like the blue and red curves are reflected through the line y equals x, right? As in fact they are. So how about cosine? Well, I'm going to say here, if x is between 0 and pi, then give me cosine x. Right, so that looks like that, right? And then I want to graph also the arc cosine or the inverse cosine of x. And then we see that, right? So does that look like we have symmetry through the line y equals x? So let's put the line back. Yeah. Let's kind of zoom. Right, so notice that cosine is decreasing on this interval, so is arc cosine, right? They're both decreasing at the point where they intersect is on the line y equals x, right? And what is this point at the top? Well, that's if the input to arc cosine is -1, then the output is pi. Just like on this green curve, if the input is pi, then the output is -1. So, you know, that's the reflection through the line y equals x of those 2 points. Yeah, similarly, if the input to cosine is 0, then the output is 1. If the input to arc cosine is 1, then the output is 0. Right, that's those 2 points there, the other extreme. And the halfway point, well, the cosine of pi/2 is 0, so the inverse cosine of 0 is pi/2. That's this point up here. All right, questions about all that? Leonardo is here. Good man. I will make a note that that is so. Which gotta get to the right place. Yeah, oh, okay, so I had you already. I guess that was a while ago, huh? All right, so, okay, so no fresh comments. Yeah, Kyle, I think I got you. Did I? Moreno. Yeah, yeah, definitely. Okay, so, all right, so with that, let's go back to the text and see what we got there. More problems, huh? So they want you to use a calculator? Sure. Do we have a calculator? Maybe. Yeah, here's the Texas Instruments. It's a little bit awkward because, you know, I can't seem to figure out how to get the mouse to line up properly. I have done it before, but oh well. Anyway, so we got to turn it on. We want to clear the input. Oh, I guess we want to exit out of where we were. And then we want to make sure that we're in the proper mode, right? So we're in radian mode. That's the mode you want to be in for using these inverse functions, generally speaking. Yeah, we'll also go into degree mode. We're gonna need this to solve triangles, and so you can be in either. So let's try it in both modes. So we're currently in radian mode. That means that we're going to get the length of the arc instead of the degree measure of the central angle that arc subtends. So let's see. So if we get out of here, and I say they want the arc that will take us to a cosine of negative. So I go second cosine, that'll take me to usually this is the way it works on a scientific calculator, right? The cosine key has a shift value, which is the inverse cosine. So when you hit second first and then cosine, you get the inverse cosine function. And I guess I want, use the keys. And it's the inverse cosine, let's say, of negative 0.9 2761, whatever. And close the parentheses and then enter. So it says that arc is 2.7587, etc. Right? Does that make sense? Well, let's go to the unit circle and see if we can make sense out of that. Unit circle being here. Up here. I guess we can reuse this one, right? So if cosine is negative 9 point something, right? And we're way over here. So let's suppose that this is negative 0.9, what was it, 92761. So there's 2 points on the circle corresponding to that, but only one of them is in the interval between 0 and pi, and that's this one up here, right? And so what are the coordinates here? Well, apparently the x coordinate here is negative negative 0.9276. What's the y coordinate there? Yeah, we can figure that out, but let's not for now and just say, look, what distance takes us to here? And that's t equals this number we just computed, 2.7588, approximately 2.7588. That is an approximation, right? And does that seem reasonable? Yeah, well, pi is 3.14. So you go a little bit further, you get to pi where cosine is negative 1, right? So what's the y coordinate here? It's sort of a little follow-up question. How do you get that? Well, you look at, can we use the space over here? Sure. The equation for the unit circle is x squared plus y squared equals 1, right? The distance to the origin, or the square of the distance to the origin is 1, which means the distance to the origin is 1, right? So if x is negative 0.9276, can we solve this equation for y? You betcha. Can we use the calculator? Well, I got it handy here. Let's say, yeah, I want to say, give me, and it doesn't matter whether it's positive or negative when we square it, right? So if I square this thing, I get 0.8604. And if I subtract that from 1, how do you do that? Well, you can say 1 minus, and then there's a key that says the entry. Oh, I screwed that up, I guess. 1 minus, oh, it's this key here, the previous answer. And that's the square of y, right? So I want the square root of that. So I'm going to say second square root button somewheres. You can't see the keys, but yeah, there's a square root. And I'm going to say the square root of that last thing. And so I get about 0.3736. And I'm going to write that on my sheet here, right? So this is 0.3736. Does that seem like in the ballpark? I think so, right? If you were to follow this over, you'd get to here, which is, you know, like a third of the way up, right? In the neighborhood of a third of the way up to 1, right? Okay, so that means that the sine of the angle whose cosine is 2.758, oh, sorry, negative 0.9276. The sine of the angle whose cosine is negative 0.9, etc., is 0.3736, right? All righty, let's see what other kind of problems they have for us here. Simplifying expressions involving trigonometry. Yeah, so this is the same sort of thing, right? I was kind of anticipating that they might do this. So let's do, say, number 24, the cosine of the angle whose cosine is 2/3. Well, do we even have to discuss that? I mean, do we even have to write anything down? We can discuss it. Obviously, we are discussing it. But the angle whose cosine is 2/3 is the angle whose cosine is 2/3. So the answer to that is 2/3, right? It's like asking, who's buried in Grant's tomb? Well, you're telling me, what is the point that you're asking me? How about, what happens if you take the sine of the angle whose, the arc that takes you to a sine of y 5 on the unit circle? Well, there is no such thing, right? So in 26, the arc of on the unit circle that takes you to a y coordinate of 5 does not exist, right? Because there is no y coordinate of 5 on the unit circle, right? So the domain of the inverse sine function is between -1 and 1. If you have a large value outside of that, then the inverse sine is not defined. How about the tangent of the angle whose tangent is 3/2? Well, that's obviously 3/2, right? How about the sine of the angle whose, I keep saying the angle, which I'm in the habit of saying that, but for our purposes, we're thinking of the arc. Now, in radian measure, arc and angle are numerically the same, so it works for radian measure of an arc, of an angle. So the arc that takes us to -3/4 is going to be negative something, right? That's not a well-known value, but if we take the sine of that value, we're going to get -3/4, right? So that's all kind of silly. There's not much to compute. I just think, does it make sense? So over here in 31 through 46 here, we've got more of these, right? So what is the arc that takes us to a place where the cosine is pi/4? Well, that's going to be pi over 4, right? So again, these are all just sort of, are there any that where you can't just say, well, the function and the inverse function outdo each other, right? I think here, right? So be careful on 42. Let's put 42 on the workbench here. Because there's a little bit of an issue there. We have space down here? Yes, we do. So this is 5.5, I believe, is where we are in the text. Or is it 5.4? 5.5. 5.4 was the more trigonometric functions in their graphs, right? So number 42, we want the, so 5.5, number 42. We want to take the, what is the arc that takes us to the place where we have the sine of 11 pi over 4? Well, let's dial up sine of 11 pi over 4. Where is 11 pi over 4 on the unit circle? Well, it's more than 2 pi, right? So 8 pi over 4 is 2 pi. So we go once around, and then how much further? Well, 3 pi over 4 further, and 3 pi over 4 is over here, right? So this is the point coterminal with 11 pi over 4. It's also 3 pi over 4, right? Those are coterminal points. Where y is positive, right? So could we say that the arc that takes us to a point where the sine is, well, let's simplify this, right? So I'm going to say, what is the sine of 11 pi over 4? What is the y coordinate here, right? Well, the y coordinate here is square root of 3 over 2, right? Oh, sorry, no, daft. Square root of 2 over 2. It looked like it was too high up to be, but yeah, it's 0.707, that's about right. Right? So should we say, yeah, that's 3 pi over 4? No, because 3 pi over 4 is not in the range of allowable values. Remember, the range of the arc sine function is negative pi over 2 to pi over 2. So is there some arc in that range that would take us to this y coordinate, right? And yes, there is, right? It's over here. And what is, that's pi over 4, right? So shall we say, yeah, this is the arc between negative pi over 2 and pi over 2, if you were to add the, complete description, that takes us to root 2 over 2, that's pi over 4. So it's not even a coterminal position with 11 pi over 4, but it is a position with the same y coordinate, right? And that y coordinate has got to be less than pi over 2, which pi over 4 is. It's half of pi over 2. Okay. How about the sine? This is number 48. I'll do a little bit of a carriage return here. For number 48, we've got the sine of the arc that takes us to a tangent. Sine of the arc that takes us to a tangent of negative root 3. Well, I'm going to rewrite this as the sine of the arc that takes us to a tangent of negative root 3 over 2 over 1/2. Why do that? What have I done? Well, it's true that negative root 3 is the same as, divide the numerator and denominator by 2, right? So you get negative root 3 over 1. That's the same as negative root 3 over 2 divided by 1 over 2, right? So why bother? Well, because that makes it explicit that the sine is negative root 3 over 2 and the cosine is 1/2. And where is that? No, let's dial it up on the unit circle. So the sine is negative. That means we're down here. And we're right here. So x is positive 1/2 and y is negative root 3 over 2. What arc is this then? That's negative pi over 3, right? Okay, so that means that this is equal to the sine of negative pi over 3. And what is the sine? Well, we just sort of said the sine there is negative root 3 over 2, right? So yeah, it's sort of a three-step process maybe. Figure out where you are in the unit circle, make sure you're within the range of your inverse function, and then use that as the input to the outer function sine here, right? Okay. Back to the text, I think. Yeah. Modeling harmonic motion is the next topic, wherein they have a preamble. What do you call it when you're reading the text? Yeah. There's a word I'm trying to think of, never mind. So periodic behavior that repeats over and over again is a sign of insanity. No, it's periodic behavior. Insanity is when you do the same thing over and over again, expecting a different outcome. And periodic behavior is common in nature, that we have the seasons, we have, the hours, we have days, right? That's periodic. Seasons are periodic. Phases of the moon are periodic. The tides are periodic, more or less. Daily rate rising and setting of the sun, which results in a repetitive pattern of day, night, day, night. Another example is the daily variation of the levels at the beach, tide levels at the beach. Results in repetitive pattern of high tide, low tide, high tide, low tide. Actually, there's neap tide and whatever the other tides are. Certain animal populations, so there's like a high low tide and a low tide, whatever. Certain animal populations increase and decrease in a predictable periodic pattern. Is that true? Interesting. So they're getting into wildlife biology. A large population exhausts the food supplies. They're explaining why this would happen, right? So the large population exhausts the food supply, which causes starvation, which causes a small population size, which results in plentiful food supply, which causes the population to come back. And yeah, so there's a little predator-prey model we can investigate here. Other common examples of periodic behavior involve motion that is caused by vibration or oscillation. A mass suspended from a spring that has been compressed and then allowed to vibrate vertically is an example. But back and forth motion also occurs in such diverse phenomena as sound waves, light waves, alternating electrical current, pulsating stars, to name a few. In this section, we consider the problem of modeling periodic behavior. All right, so you see here's a spring mass system. So as time goes by, the mass goes up and down, following the shape of the sine wave, right? And so essentially we're going to see the same ideas we've seen before with some new names, right? So now instead of having that generic input x, the input is omega t, where omega is the factor that determines the frequency. It is not the frequency. The frequency is the reciprocal of the period, right? But omega you can think of as the angular velocity is what I want to say. The velocity at which you travel around the unit circle, right? And so, you know, if you're traveling around the unit circle at a speed omega meters per second, you multiply that by number of seconds, and you have the distance you've gone around the unit circle, and that's the input to the sine or cosine function. And so the period is 2 pi divided by omega. So before we had a factor of b there, I think. And so we said it was 2 pi over b. So we just simply renamed that parameter omega, the Greek letter omega. It looks like a W, I know, but it's actually the Greek letter omega, which is commonly used in the business to represent what you might call angular velocity, or the speed at which you travel the arc of the unit circle. The frequency is just the reciprocal of the period, and the amplitude is the absolute value. We want to think of the amplitude as positive, right? So if A is negative, that means you've got some kind of a reflection. So note that if you were to put a factor of 2 pi in there, then so you'd have 2 pi divided by that is going to be 1 over v, and the reciprocal of that is v. So the frequency becomes, actually it's not a v, it's a nu. Nu is the name of that Greek letter. Since we can immediately read the frequency from these equations, we often write the equations of simple harmonic motion in that form. Instead of having omega t, you put in 2 pi nu t, where nu is the frequency. Okay, so to give you an example of a vibrating spring, vibrations of a musical note. So should we analyze this function? Well, they're going to do it for us here, right? So they're saying, here's the amplitude, here's the period, which is 2 pi divided by the coefficient of the input t, right? Which here is 80 pi. So 2 pi divided by 80 pi is 1/40th. So the frequency would be the reciprocal of that, which is 40. So 40 vibrations per second. Is that audible? That's a very low audible tone. Yeah, I'm tempted to go to a web page where we can hear this. Is this possible? Maybe let's take a quick gander and see. Okay, so I'm going to search for an app that will allow us to hear tones at various frequencies. I should have searched for this earlier, right? So we wouldn't be, where are we? I want to make sure I'm picking the right browser. So let's go out here and say, here, frequency. I don't know, what else to say? How do you search for this? Hearing range, normal hearing range. Sounds you can't hear but can still hurt your ears. What can you hear? High frequency, low frequency. What sounds can people hear? Yeah, so I want to actually an app that will do that. I don't want it to be a phone app. It's on Google Play. All right. Frequency sound generator. That's what I want. Is this going to do it for us? Oh. All right. No. So I want, sorry, frequency sound generator. Windows 10. How about that? Can you do it for Windows 10? Microsoft Store. I don't want to buy one. I just want you to do it for me. All right. So is this? We have to download the tone generator for Windows. Okay, I'm going to be brave and do this. Oh, all right. I don't know what the terms are. We're going to assume that they're good. All right. Now I want to have a window for this, right? So I'm going to say add a window for tone generator. Okay, and yeah, okay. So we now have this window, and we can look at it together. I guess we are looking at it together. Let me bring it up. So these are very low frequency. You can't hear these. That's very high frequency. Oh, I see. So where's the play button? Yikes, that hurts. So let's get rid of one of these frequencies, shall we? Remove tone, remove tone. Okay, I want to edit. Okay, I guess we have to have at least one tone. So that's very high. Can we change that to something not quite so high? How about 400? 400 hertz. I think that's the A below middle C. Yeah, that's the A below. All right, that's not quite sure what I'm hearing. Okay, so then I'm going to add another tone. I'm going to make it 440. I think is the A below middle C. But I'm going to change this to an 800. That's an octave higher. So we're hearing both 400 hertz and 800 hertz. And if I go another 400 hertz, let's see, add tone 1200 hertz. Oh, not this one. Yeah, so you're getting a combination of different frequencies and it makes a sound, okay. Let's say we did that and let's jump to the exercises because let's see, we've got this now the 13th hour. So to do that, I will go here and say, get rid of the tone generator and go back to text and yeah, so these are, this is the general sort of waveform. So you got a horizontal shift, you got a vertical shift by B, and you got an amplitude A. So you're oscillating between, A less than B and A more than B. That's the amplitude of oscillation, centered on the equilibrium of B. And you've got a wavelength. So the shift is C, and then a wavelength of 2 pi over omega, right? So you get one complete waveform. And so you've got damped harmonic motion. We're not going to cover that because it involves exponential functions, which we are not allowed to bother with. So using phase, okay. I think basically this will just give us a chance to review graphing periodic functions, right? And so here's a bunch of them, right? So we've already done a lot of problems like these, right? But let's do it again. Hey, how about 36? Okay, so the instructions here are a pair of sine curves with the same period is given. Find the phase of each curve, find the phase difference between the curves, determine whether the curves are in phase or out of phase, and sketch both curves on the same axis. So what does it mean for them to be in phase? Well, that could be, if they're out of phase, if they're completely opposite, then they cancel each other out, right? So in number 36, both sine waves have an amplitude of 15. They both have a period of pi, right? The coefficient of t is 2, so 2 pi over 2 is just pi. That's the wavelength or the period. And the shift is going to be pi over 6 for the first one and pi over 12 for the second one. Do you see that? Factor out the 2 and you've got pi over 6 shift to the right. The second one, factor out the 2, you got pi over 12 shift to the right. So let's go ahead and let's just, since we're short on time, let's go to GeoGebra and graph it there. Okay, so we've got our inverse functions. So should we save this? Or do we care? Let's file save it. And then we'll say new. And we're going to say 15 sine twice x, because it's got to be x, right? Minus pi over 3. So you see the amplitude of 15 there? Yeah. So it's oscillating between, the equilibrium is at 0, right? So it's oscillating between negative 15 and positive 15. And the shift is pi over 6. Shall we plot point pi over 6 comma 0? Right there, right? So that's the shift, right? So one complete waveform will be from there to pi over 6 plus pi. Yeah, that's one complete waveform. And then let's plot the other one, which is 15 sine of 2x minus pi over 6. So would you say these are in phase or out of phase? So notice that I said that there should be, I think I did this wrong, right? It's supposed to be a pi over 6. Okay, so those, yeah, so you can see that there's a shift to pi over 6 now, right? Or pi over 12, right? So if I go pi over 12, 0, that's the starting point. If I add pi to that, which is also the wavelength of this thing, right? And I get the end point of that one, right? And I would say these are more in phase than out of phase. When I add them up, the amplitude of the combined waveform is going to be larger than the amplitude of either one, right? Right, so that means that they're in phase, right? So you superimpose these, you get another sinusoid with the same period, right? And its phase is going to be half the distance between those. So I think that, you know, pi over 8, I want to say. What's the amplitude of this thing? So what's halfway between pi over 12 and pi over 6? Well, 3 pi over 12 divided by 2 is pi over 8, right? So if I say pi over 8 comma 0, there it is, right? That's dead on where it's starting. And let's drag it out a little bit so we can see a little bit better. But the period is the same as the period, right? So it's finishing, you know, in the same distance that the other two were, right? So we haven't changed the period, but we have changed the phase shift, and we've changed the amplitude, right? So the new amplitude is more like, oh, what would you say, 30 about? Can I plot a point up here? Yeah, that looks pretty close to 30, huh? Maybe a little bit less. I think it's going to be square root of 2 times 15. What is that? 15, and you have no way of knowing. I don't know. But oh, that's twice what I want, right? So it should be square root of 2 over 2. Oh. That's 21. That's too small. So, well, anyway, yeah, yeah, they're both sine, right? So I'd have to do a little envelope work, but yeah, we're getting close to the end here. So yeah, how would we find the amplitude of this thing? So let's go to a little sheet of paper. Work. Do I have a sheet of paper here somewhere? Yeah. So if we have 15 sine of 2t minus pi over 3, and we add to that 15 sine of 2t minus pi over 6, we can factor out the 15. What do we know? We know that cosine of t is equal to the sine of pi over 2 minus t. Is that true? They're off by pi over 2, right? I think that's true. Sine. Yeah. Right. That is true. So will that help us here? So if I say, if I have pi over a factor of pi over 2 in here, that, but we can also say the sine of t is equal to the cosine of pi over 2 minus t, right? These are the complementary identities. And so we can, instead of the sine, we can subtract. So we can say this is 15 sine of 2t minus pi over 3 plus 15 cosine of pi over 2 minus this. And if you subtract, you know, this, so, well, let's just, yeah, 2t minus pi over 6. You might wonder why I'm doing this. I know how to combine sine and cosine this way, right? So that's why I'm trying to write the sine in terms of cosine, which we can do by using this complementary identity, right? And so what does that get us? Well, we're adding pi over 6 to pi over 2, and pi over 2 is 3 pi over 6, and we get 4 pi over 6, or 2 pi over 3, right? And cosine is an even function, so I can say this is the same as 2t minus 2 pi over 3. Should we check that? Oh, we're out of time, aren't we? Yeah. We could check that in GeoGebra by plotting cosine of 2x minus 2 pi over 3 and seeing, oh, we want 15 times that, right, to be the same as what we had. 15 times that. Okay, yeah, you see that's exactly the same as, which one is it? Not this one, but this one. Yeah, those are the same function, right? And then we could see about combining those, but that's getting a little bit far afield, I think. Sorry about that. So that takes us to the end of chapter 5 almost. You know, there's a lot of neat applications in here for you to explore and discovery. But yeah, so on Monday we'll review, and Tuesday we'll test on chapter 5. That'll be week 12, so not a moment too soon. We still have to talk about solving triangles, and I think we may just like go very quickly through chapter 6, because chapter 6 is essentially a reprise of chapter 5. So we'll just, highlight the new things in chapter 6. And I think one of those things is going to be solving triangles using inverse functions, okay? So yeah, look forward to that. And we can, if you go back, sorry, I'm going a little bit over here. If you go back to, sorry, there we are. Okay. I need to pick this up here. Right. Where's my mouse? The mouse has disappeared. Oh no. Okay, there it is. Yeah, so are we looking at this? Yes. Okay. So there is this old exam here, right? Oh. So let's talk about this. So work on this over the weekend as a way of preparing for the exam, and we'll talk about the solutions on Monday. Any questions about anything at all before we adjourn? I'll be in the Math Science Study Center this afternoon between 2 and 4. At which point,
thank you.
Okay, great. At which point I'll get in my chariot and return to the desert. And not that anybody would know the difference, right? Well, actually, I'll be less echoey and I'll have my proper docu-cam back. So that will be noticeable. All righty. Okay, so there are instructions, I think, somewhere here for how to join me in the Math Science Study Center. Where is that? Here, right? So if you click on that, oh, it wants to actually launch the meeting. Huh? That's crazy. No, I don't want to launch a meeting. What did I do? Oh, this must be an actual hyperlink to that, right? Did I not? Oh yeah, I put the schedule here, right? But that hyperlink will actually take you right there, huh? And you can see that there are people available there at all times of the day, right? Okay. Well, I'm not sure what happens between 2 and 2:30 on these days. I guess if you go there at 12:30, if you go there now, there won't be anybody, but in 20 minutes or 15 minutes now, there will be Susan Najati, who I don't know, but maybe she's a scientist. Suzanne, or maybe he, right? It's not Susan, it's Suzanne. So yeah, go find out. Bother these, make them earn their money. Okay. All right, so I'll wrap it up here and wish you a pleasant afternoon and a very nice weekend.
Thank you, Professor. Have a good afternoon.
You too. Let's see.